Hello physics students. Here is your kind of teaching video, if you will, for your concept development practice page 5.1. Again, you are welcome to do this with me, okay, as I do this. So number 1 says, above left, use the scale 1 centimeter equals 5 meters and draw the positions of the drop ball at 1 second intervals. Neglect air drag and assume g equals 10 meters per second squared. Estimate the number of seconds the ball is in the air. So it's asking us to draw the position, and our equation for position is distance is 1/2 gt squared. So that's 0.5 times 10 meters per second squared times our time squared. Okay, so at 1 second, and it asks us to do 1 second intervals. So 0.5 times 10 times 1 squared gives me 5 meters. And my scale is 1 centimeter is 5 meters. So I'm just kind of using this to kind of help me make straight lines. Okay. Here's my ball. This is 5 meters, okay? And I'm just going to put that on there because I just did that calculation. Next, I want 2 seconds. So 0.5 times 10 times 2 squared is 20 meters. So 1 centimeter is 5 meters, so that's going to be 4 centimeters. So at this 4 centimeter mark, that's where my ball is this time. And this distance here is 20 meters. Okay. Now we want to do 3 seconds. So 0.5 times 10 times 3 squared is 45 meters. And my scale is 1 centimeter is 5 meters. So to figure out how many centimeters that is, I'm going to divide it by 5. So that's 9 centimeters. So at about 9 centimeters, about right here, is my ball. And again, we said that this time this was 45 meters. All right, we're not at the bottom yet because we want to know how long the ball's in the air. So, okay, we're going to go another second, right? So this was t equals 1 second. This was my time equals 2 seconds. Here is my time equals 3 seconds. So now we're going to try 4 seconds. So 0.5 times 10 times 4 squared is 80. And if I divide that by 5, that is 16. So now I'm right here. T equals 4 seconds. And this distance here is 80 meters. So, estimate the number of seconds the ball is in the air. 4 seconds. Above right, the 4 positions of the ball thrown with no gravity are at 1 second intervals at 1 centimeter equals 5 meters. Carefully draw the positions of the ball with gravity, neglect air drag, and assume g equals 10 meters per second squared. Connect your positions with a smooth curve to show the path of the ball. Okay, so remember, this is our law of inertia line. If we just had inertia and we threw a ball and there was no gravity, this is where it would be. But remember, what this means is the ball falls below this line this same distance each second. So at our first position, we're going to be at that 1 centimeter mark. Okay, so here's my ball. And this distance is 5 meters. And this is my t equals 1 second. Now, at the time of 2 seconds, it's still going to fall the 20 meters. So it's going to be at the same position vertically. Okay, so about right here. Okay, So here's my t equals 2 seconds, and this distance here, okay, is 20 meters. Okay, so it's going to fall the same distance, the 45 meters this time. Okay, so it's about somewhere in here, and I'm going to just kind of see where this is here. So we're going to say it's about right here. Okay, so there's my t equals 3 seconds. And again, this distance here is 45 meters. Notice the distances are the same, okay, as when it was free fall. So at this position, right, it's going to hit the ground again. Okay, t equals 4 seconds, and this distance here is 80 meters. So now I've done that, right? I've drawn the positions of the ball with gravity. Now it wants me to connect my points with a smooth curve. So it kind of means that from my start, as smooth as it's possible for me to do, I'm going to show the path of that projectile. How is the motion in the vertical direction affected by the motion in the horizontal? So what it's saying is, did the fact that this ball was also moving horizontally affect how far it fell each second? And notice it didn't. My distance is exactly the same as it was if it were in free fall. So we kind of want to answer that it doesn't, okay? Vertical direction motion is only affected by gravity. So horizontal motion does not affect, it should be an A instead of an E, vertical motion. When we compare it to that ideal in law of inertia line, okay, it falls the same distance. This time the ball is thrown below the horizontal. Use the same scale, 1 centimeter equals 5 meters, and carefully draw the positions of the ball as it falls beneath the dashed line. Connect your positions with a smooth curve. So again, you guys, the distance it falls here is going to be the 5 meters, right? So, okay, but it was thrown downward, and this is kind of at 1. So it's going to fall 1 more centimeter. So it's going to be, okay, about right here. So this distance again is 5 meters. This is my time equals 1 second. I'm going to put those times off to the right. So now the ball is going to fall, right? We know how far it's going to fall. It's going to fall 20 meters below that line. So 20 meters. So here is that line to begin with. And I think maybe it's at 2. So 20 meters means it's going to fall. 20 divided by 5 is 4. It's going to do 4 more centimeters, so that's going to be at the 6 centimeter mark. Just want to make sure I'm doing it right. Yep. Okay, so here's that ball. And I want to be at the 6 centimeter mark, so about right here, we'll say. Okay. So this is my time equals 2 seconds, and this is 20 meters. My next second is going to fall 45 meters, which is 9 centimeters. Okay. So wherever this is to begin with, which looks like it's at the 3 centimeter. 3 plus 9 is 12 centimeters. So I should be at the 12 centimeter mark and about straight below it. So maybe about right there. Time equals 3 seconds. This distance is my 45 meters. Okay. Next, we know it's going to fall 80 meters, which was 16 centimeters. Right? So I'm at about 4 plus 16 would be 20. So I don't know that this is really the same way it was. So we'll see here. I don't know if it was really 4 centimeters on this because it printed. Oh, no. So about 3.5 on this. So about 3.5 more. It's about right here. So basically where this writing is and below that ball gives me about right here, okay, is my time equals 4 seconds. And this distance here, right, that's that 80 meters. And then it wanted us to make a curve. Okay, so we're kind of playing connect the dots. Estimate the number of seconds the ball remains in the air. Well, it doesn't make it to 4 seconds, right? It would hit the bottom. So maybe about 3.5 seconds. Okay. Based on our picture. Number 4. Suppose you are in an accident. Suppose that you are an accident investigator and you are asked to figure whether or not the car was speeding before it crashed through the rail of the bridge and into the mud bank as shown. The speed limit on the bridge is 55 miles per hour equals 24 meters per second. What is your conclusion? Well, okay. Notice where it went 24 meters horizontally and not even 5 meters. So it should have fallen, okay, in 5 meters, 24 meters. Okay? So we know that it went about 24 meters in 1 second. We know this is 1 second because this is about 5 meters, and that's how far a vehicle falls in 1 second. Okay? And our horizontal distance is 24 meters. So it was going the speed limit. The person who wrote your CDP says the car was traveling at 24 meters per second after it crashed through the rail. And again, we know that because 1 second's worth of fall and it went 24 meters left to right, which means it was speeding. Therefore, it must have been traveling faster than 24 meters per second before hitting the rail. Because it lost some speed going through the rail. Therefore, the driver was speeding. So this might be the type of math that a person on the state police might do, or county police, to try to determine whether or not this person deserves a ticket for this accident. So I hope that helps you with this concept development practice page. Have a great day, and I'll talk to you tomorrow.